Dear classmates, welcome back to the DFT chapter. In the previous video, we have introduced the concept of flip-flop based scan and latch based scan. Now, in this video, we will introduce the whole scan design flow. This slide shows the scan design flow taken from the W textbook. The scan design flow converts the original design into a scan design. First of all, we will check if our original design obeyed the scan design rule. If there is any violation, we will need to repair them. After we fix all the violations, we will have a testable design. And then we can proceed to the scan synthesis, which has 4 small steps: scan configuration, scan replacement, scan reordering, and scan stitching. During the scan synthesis, we would also need layout information from the physical design and the constraint and control information from the designer. After all these steps, we now have a scan design which has scan chain inserted into our original design. Then we can start our test generation. After test generation, we can do scan verification to make sure that the test pattern can be correctly applied to our design. So now let's start from the first step: scan design rule checking. Scan design rule checking makes sure the design obeys our rules so that the scan chain can be inserted correctly. The EDA tools are now very smart, so they can automatically fix the violation after design rule check. There are many scan design rules. Some examples are shown in this table. For example, the first DRC rule is that if we have tri-state bus in our design, we should fix the bus contention during scan shift. And if we have bidirectional I/O pins, we should force it into an input mode or output mode during scan, and etc. There are many scan design rules, so we will only show 4 examples in this video. Please note that these rules can vary for different tools and different companies. Now let's introduce the first design rule: tri-state bus. Suppose that we have a tri-state bus in our original design. This bus has 3 drivers, D1, D2, and D3. The enabled signals are controlled by scan flip-flop 1, 2, and 3. This seems to be a correct design. However, when we shift the scan chain, we can have random patterns coming in. So we can have more than 1 drivers driving this bus at the same time. If these 2 drivers have different values, then we will have a contention. This is not allowed during scan shift. So what should we do? We can simply repair the design in this way. We insert some extra logic so that when scan enable is 1, we make sure that driver number 3 is not driving and the driver number 2 is also not driving. Only driver number 1 is driving this bus. So there is no bus contention when scan enable is 1. We can also insert this bus keeper, which are weak inverters cross-coupled so that we can have a fixed value when there is no bus driver. So we guarantee that this bus is not in a high impedance state. DRC number 2, bidirectional I/O pin. Suppose that in the original design we have a bidirectional I/O pin. When the value of Q is 0, this buffer is turned off. So this is an input pin. When Q is 1, this buffer is driving the output. So it's an output pin. This seems to be a correct design. However, when we perform a scan shifting, we have random 0, 1 coming into our scan chain. So this pin can be input sometimes and output sometimes. So this random behavior is not what we want. We can simply repair this circuit by inserting this simple logic. When scan enable is 1, this output driver is always turned off. So this is always an input pin when scan enable is 1. Gated clock is a very typical low power technique. In this example, we have a very simple clock gating logic. When enable is 0, the gated clock is always 1, so the clock is turned off. On the contrary, when enable is 1, the clock will be turned on. However, this is not a very good design, because we can have hazards coming out from this enable logic. If we have hazard, then we can have hazard at the gated clock output, which is not a very good thing. So we should change our clock gating circuit in this way. We will insert a flip-flop here, which is a negative H trigger flip-flop. At the falling edge of the clock, we will sample the value of enable. When enable is 1, the following clock will be turned on. When enable is 0, then the following clock will be turned off. So this is a better design than the previous one because it can handle hazard. It seems to be a good clock gating circuit. However, the problem is that when we scan this flip-flop, the clock can be randomly gated during scan shift. So we cannot control the values of the following flip-flop. This is a big problem for scan. So how can we fix this? So in DRC number 3, we need to repair this circuit so that when scan enable is 1, we want to make sure the clock is always on. Suppose this figure shows the original design, where we have a negative H trigger flip-flop that generates an enable signal. Then we have a gated clock signal. We need to repair this circuit by adding one extra OR gate. So when scan enable is 1, this flip-flop is always 1. So the clock is always on when we perform scan shifting. So we can make sure that this flip-flop can be correctly shifted. when scan enable is 1. DRC number 4, combinational feedback loop. Normally, we don't have combinational feedback loop in our combinational circuit. But if in the original design we have this combinational loop, this would create sequential behavior in test mode, and we cannot control the value of this circuit. And we know that sequential ATPG is very difficult. So if we want to avoid sequential ATPG, we need to repair this combinational loop. We can simply inject this small circuitry. When test mode is 1, we can directly control the value of D. So we can use combinational ATPG to generate test patterns. So here is a review. When test mode is 0, this circuit is in normal operation mode. So the behavior of this circuit is the same as the original design. When test mode is 1, scan enable is 1, we perform a scan shift. When test mode is 1, scan enable is 0, we perform a scan capture. Please note that we use the test mode signal instead of scan enable signal in this repair, because we want to make sure that in scan capture mode we can still control the value of this combinational feedback loop. That is why we use test mode instead of scan enable here. Now please work on this quiz. Suppose that we have this asynchronous reset in this flip-flop. The reset signal is coming from scan flip-flop number 1. This is a good design. However, in test mode, we can have 0, 1, 0, 1 random bits coming in to scan flip-flop number 1. In this way, scan flip-flop number 2 can be randomly reset during scan shift. So now please prepare this circuit so that there is no reset occurred when scan enable is 1. Please now pause the video and work on this repair. Okay, have you done? The answer is very simple. We just insert this extra logic so that when scan enable is 1, this pin is always tied to 1. So scan flip-flop number 2 is not reset during scan shift. Have you got it correctly? Suppose we have already repaired all the design rule problems. We now have a testable design which is ready for scan synthesis. Scan synthesis is also known as scan insertion or DFT insertion. Scan synthesis can be broken down into 4 small steps. In the first step, scan configuration, the designer can decide the number of scan chains, and the designer can also specify which flip-flop to exclude from our scan chain. For example, in this figure below, suppose that the designer decides to have 1 scan chain, and the small green rectangle indicates original flip-flop, and the designer decides that we don't want to include this special flip-flop in our scan, and the other flip-flop should be included in our scan chain. In the second step, scan replacement, we will replace the original flip-flop or latch in the testable design with their functionally equivalent scan cell. For example, we would replace the original flip-flop into a scan flip-flop, which is larger. And in the third step, scan reordering, we will reorder the scan cell based on the layout information to minimize the routing wires. And in the fourth step, scan stitching, we will connect all the scan cells to form scan chains. In this example, based on the location of the flip-flop, we will reorder the scan cell 1, 2, 3, 4, 5, and then we will stitch them into one scan chain. In this way, we can insert a scan chain into our testable design. Although these 4 steps look very simple, there are many details that we need to take care of. In the following slides, we will discuss these details. If we have a scan chain that go across different clock domains, we need to be very careful. Suppose that we have one scan chain that goes through clock domain 1 and the clock domain 2. Ideally, this scan chain would work perfectly if we connect clock 1 and the clock 2 together. If there is no clock skew and the 2 clocks are perfectly synchronized, then we can transfer the data without problem. However, in practice, there are big clock skews between 2 clock domains. In the first case, suppose that the clock 2 is slightly ahead of clock 1. Let's say the clock 2 rising edge is before the clock 1 rising edge. In this way, the data will be transferred from scan cell P to scan cell Q at the rising edge of CK2. And then at the rising edge of clock 1, new data will be shifted in to scan cell P. And we can repeat this without any problem. So in this case, the scan cell works fine. However, consider the second case where the rising edge of clock 1 is ahead of the rising edge of clock 2. At the rising edge of clock 1, the new data will be shifted into scan cell P. At this time, clock 2 is still not active, so the data will be missing. At the rising edge of clock 2, we will shift the new data into scan cell Q, but at this time, we will miss the old data in scan cell P, so this is not okay. So how can we fix this problem? So when we stitch a scan chain across different clock domains, we need to insert the additional flip-flop called lockup latch. A lockup latch is a negative edge trigger flip-flop in the middle of 2 clock domains. When we have a scan chain that cross different time domains, we need this lockup latch in the middle. to transfer the data correctly. As is shown in this timing diagram, suppose that clock 1 is slightly ahead of clock 2. At the rising edge of clock 1, D1 data is shifted in. At the falling edge of clock 1, the lockup latch would be triggered, so the data would be transferred to the lockup latch. And then at the rising edge of clock 2, the data will be then transferred to clock domain 2. As is shown in this timing diagram, with the help of the lockup latch, we can now safely transfer the data from X to Y, then to Z successfully. So we are not afraid of the clock skew problem anymore. So the lockup latch is a very important DFT technique when we insert a scan chain. In addition to the lockup latch, there are actually many practical problems when we insert scan chain. Due to large clock skew, data from different clock domains cannot be captured together. This figure shows a graph of a design which has 7 functional clock domains, CD1 to CD7. An edge indicates data transfer across different clock domains. For example, we have data transfer from CD1 to CD2. Because there are large clock skew between CD1 and the CD2, so CD1 and the CD2 cannot be stitched in a single scan chain. We need to separate them in different scan chains. Similarly, we have data transfer from CD1 to CD3. So CD1 and the CD3 cannot belong to the same scan chain. However, we can assign independent clock domain as one clock group. For example, there is no interaction between CD2 and the CD3, so we can group them together. And the flip-flops in these two clock domains can form a single scan chain. Similarly, CD4, CD5, CD6, CD7, they belong to clock group number 3. We can insert scan chain that belong to these clock domains, but we cannot insert a scan chain that cross different clock groups. If you want to know more details, please refer to the WWW textbook about clock grouping. Okay, now suppose we have replaced all the flip-flop into scan flip-flop. Now we can start to reorder the scan shells based on the layout information. Currently, the EDA flow is like this. We will first place the logic gates and the flip-flop based on the functional timing requirement. As is shown in this figure, the blue rectangles represent logic gates, and the numbered rectangle indicates the scan flip-flop, and the number is the original order in the scan chain. As you can see, this is not a very good ordering for scan chain routing. If we scan in from here, we will need to route to scan cell number 1 and 2 and 3 and 4, 5, 6, 7, 8. This is apparently a very bad routing because we go back and forth. So we can actually reorder our scan cell to save our routing wires, and then we can route the functional signal and the scan chain in a more efficient way. As is shown in the right hand side, we reorder the scan cell in this way so that we can scan into 1, 2, 3, 4 and 5, 6, 7, 8 and scan out. This is a more efficient way to route our scan chain. However, when we reorder the scan cells, we need to take care of one thing. When we have mixed negative and positive age trigger flip-flop in a scan chain, it is okay when the negative age trigger flip-flop is before the positive age flip-flop, but not vice versa. As is shown in this figure, we have a negative age trigger flip-flop before the positive age trigger flip-flop in a scan chain. At the falling edge, we will scan in the data D1. At the rising edge, we transfer the data to scan cell number 2. In this way, the data is shifted in the scan chain without any problem. You can also confirm that scan capture mode can be also correctly operated. Now it's time for you to work on a quiz. Please show that it is wrong if we have a positive age trigger flip-flop before a negative age trigger flip-flop, as is shown in this figure. Please explain the reason. The hint is that please consider the scan capture operation when scan enable is equal to 0. Please pause the video and work on this quiz. This is a more difficult one, so you might need to spend some more time. Okay, are you ready for the answer? When we consider the scan shift operation when scan enable is equal to 1, suppose we have a rising edge. At this time, scan in the data D1. D1 is ready here. At the falling edge, we can shift in the data. So D1 is now ready here. It seems like that we can operate correctly without any problem. Now let's consider the scan capture operation when SE is equal to 0. At the rising edge, we capture the data D2 at scan cell number 1. At the falling edge, we capture the data D3. And then we would assert the scan enable signal and shift out the result. At the rising edge of the flip-flop, the D2 would be shifted out. But at this time, scan cell number 2 is not ready for shifting. So D2 would be missing. At the falling edge of the clock, we would shift in a new data. So we would miss 1 bit. This is a wrong scan operation. This is why we do not allow a positive edge trigger flip-flop before a negative edge trigger flip-flop. Have you got it correctly? After scan synthesis, now we have a scan design that is ready for test generation, ATPG. You might think that our job is done, but actually it's not yet. Typically, the ATPG tool is a separate tool from scan synthesis. So, to perform a correct test pattern generation, we would need to extract the scan information from the scan design for test generation. And then after that, we need to make sure that our test pattern works correctly. So we still need scan verification. So there are two purposes of scan extraction. The first purpose is to extract the order of scan cells for ATPG, and the second purpose is to make sure that all the scan chains are correctly connected. This is needed because typically ATPG and the scan synthesis are separate tools. So ATPG need to verify the correctness of the scan design again. And then after the test patterns have been generated, we will need to verify the correctness of this pattern. We want to make sure that ATPG test patterns can be correctly applied, both in scan shift and the scan capture. For example, we can run timed logic simulation to catch hold time violation. A hold time violation means that the delay between two neighbor scan flip-flops is too small. It is smaller than the hold time of the flip-flop. Then we would have a hold time violation. So what can we do if we have this violation? We can simply insert a buffer to increase the delay between two flip-flops. In this way, we can easily fix the hold time violation. In summary, in this video, we have shown the scan design flow. Starting from the scan DRC, we need to check the original design if it has tri-state bus, bidirectional I/O pins, gated clock, combinational feedback loop, and etc. We will need to repair these violations before we have a testable design. And then we move on to scan synthesis. We can perform scan chain configuration, scan cell replacement, scan reordering, and we stitch the scan chain. If needed, we would want to insert lockup latch between two different clock domains, or we will need to insert buffer to fix hold time violation. Finally, after ATPG patterns has been generated, we also need to verify that the test pattern works correctly in our scan design. In conclusion, you might think that scan design insertion is a simple job, but actually it's not. A successful scan design is actually non-trivial. It requires a lot of work before we can make sure our test can be applied successfully. Finally, we have an FFT for you. In our previous slide, we showed that we can repair this original design by adding a few logic gates to make sure there is no bus contention when SE is equal to 1. But how about SE is equal to 0? That means how can we avoid bus contention during the scan capture cycle? Please think about this interesting question. Thank you for watching.